second. Okay. So let's start with question number 6, and this is remember summer 19 question paper 4.1. So first thing is they're asking for the enthalpy change. They're not looking for any specifics. Bond energy, it's always positive. So that's technically that's the energy that is needed to break 1 mole of bonds in gaseous molecules. And the enthalpy change of formation, it could be both. It could either be positive or negative. So what is meant by the enthalpy change of atomization? So it's the energy that is needed. So this one is also needed to form 1 mole of gaseous atoms. It's energy that is needed to form 1 mole of gaseous atoms from its element in the standard state. So that is enthalpy change of atomization. Like if you want to make 1 mole of gaseous carbon atoms from its elements, the element would be carbon solid. If you want to make 1 mole of Cl gaseous atoms from its element, the element is Cl2 gas, and there's going to be half of it. So that is enthalpy change of atomization. It's always endothermic, and the smaller the atom, the stronger would be the bonds. So the overall reaction of the atomization of bromine molecule is shown. This happens via a 2-step process. Construct a labeled energy cycle to represent this atomization process, including state symbols. Use your cycle and relevant data from the data booklet to calculate the enthalpy change of vaporization of Br2, and the enthalpy change of atomization of bromine is given. So you have to find you've got to find the vaporization. So this one is Br2 changing into 2Br gas. So first thing you're going to do is you'll have Br2 liquid, and you're going to change it into, so you're going to change this into Br2 gas. So this thing will change into Br2 gas. Now that is vaporization. That is enthalpy change of vaporization, because it's turning into a vapor. And then you have to make 2Br gaseous atoms. So you have to break you've got to break the Br2. So the next part is you're going to break the Br bond, and you'll get 2Br gaseous atoms. So this is basically the bond energy of Br and Br. Now they specifically stated that the overall reaction is known as, this is known as the enthalpy change of atomization. And they've given us the value as well. The value is 112. So this entire process, starting from Br2 liquid and ending up with 2Br gaseous, that is 112 kilojoules per mole. And bond energy, as a Br bond energy, it's also, so that one is also given in the data booklet. So I'll just quickly open the data booklet. Just 1 second. I'll just quickly, I've opened the data booklet, and I'll look for the Br bond energy, which is where it's right at the start. So the Br bond energy is given. That's somewhere. It's given somewhere. It's given as 193. So that value is provided to you. So this one is 193. So one path is equal to the other path. So what is happening here is we knew the enthalpy change of this thing that was given 112, Br2 liquid changing into 2Br gas. I wrote down the steps for this. The steps would be that you're going to take liquid bromine, turn it into Br2 gas. So you're evaporating it, and then you're breaking the Br bond to turn it into 2Br gaseous atoms. So that means enthalpy change of vaporization plus that 193, that should all total up to be equal to 100. It should total up to be equal to 112. And that will give you enthalpy change of vaporization, which is going to be what? It's going to be 112 and minus 193. Can anyone tell me what the answer is? For this one? And did you? Is it just once again?
Minus 81.
So you're getting minus 81. Let me check with the MS as well. So we're getting minus 81 for enthalpy of vaporization. And let me just double check. So this one is question number 6. And it's the first part. No, we're getting this thing 2 into 112. Okay, so we made one mistake. And that mistake, I'll tell you what the mistake is. Otherwise, the cycle was fine. The mistake was that they gave us the enthalpy change of atomization of bromine. That is for forming one bromine. Over here, you're forming, I mean, that is one thing that we missed. You're basically forming, so this is enthalpy change of atomization multiplied by 2. So that was the only mistake that we made. So we did not see that coming. Its enthalpy of atomization is for 1 mole. So you're forming 2 moles of bromine. So this entire thing was basically double the enthalpy change of atomization. So this 112 was going to be multiplied by
2.
By 2. That was the only mistake that we made. So that's about it. That was the only thing that otherwise the whole expression was the same. ठीक है, is this clear?
So तो वहाँ पे तो 2 bromine ही है. I mean, they're given 2 bromine molecules.
No, by definition, enthalpy change of atomization is when it's energy needed to form 1 mole of gaseous atoms. So when they wrote 112, enthalpy of atomization as being 112, that is for 1 mole of bromine. So in this case, you're making 2 moles of bromine. So this entire thing is basically 2 times the enthalpy of atomization. Is that clear?
Yes.
So next part is suggest how the enthalpy of vaporization of iodine would compare to that of bromine. Explain your answer. So enthalpy of vaporization. Now that is simply that in that case, if you do the same cycle, iodine is a solid. To begin with. Remember, enthalpy change of atomization is that the element turns into gaseous atoms, right? So if I draw the same cycle, the starting point would be the element in its standard state is a solid, not a liquid like bromine. You're going to vaporize it first, so it will form iodine gas, and then the bonds would be broken, and 2 iodine gaseous atoms would be formed. So the same cycle, except that the starting point would be iodine solid. So he's saying suggest how the enthalpy of vaporization of they're actually talking about iodine liquid, by the way. So they're very specific about iodine liquid. So I think they've written the state as well. So I'm just going to ignore everything else. I will not link it up with the equation of above. So it's basically iodine liquid turning into iodine gas. So is that going to have a bigger value or a smaller value compared to bromine? Does iodine have more intermolecular forces? Because when you want to turn it into gaseous iodine, you would have to break bonds. Break the
great intermolecular forces, the word behind it.
Because it's a bigger molecule, so and you have to explain your answer as well. So you have to explain that as well. So the answer is that it's going to be greater. Enthalpy of vaporization of iodine is going to be, it's going to require a lot more energy to vaporize iodine compared to bromine. And the reason for that is that iodine has more van der Waals forces. So it's got more van der Waals forces because it's a bigger molecule. So this one happens to be a bigger molecule. Now moving to the next part, what is meant by the term enthalpy change of hydration? So So it's always the energy that is released when what happens? What's the definition for this? It's energy released when
gaseous signs convert into aqueous signs.
Okay, so but when 1 mole, okay, to be specific, 1 mole of gaseous ions are completely surrounded by water and turn into 1 mole of aqueous ions. By excess water and turn into aqueous. Suggests why the enthalpy change of hydration of Br minus 1 is more exothermic than that of I minus 1. So why is Br minus 1 more exothermic compared to I minus 1?
So क्योंकि Br is a smaller atom और उस पे charge density ज़्यादा हो.
Okay, so it's a smaller ion, so it's a smaller ion and it's got higher charge density. So it's going to make stronger bonds with water. So there's more attraction. So whenever you make stronger bonds, more attraction between Br ions and water molecules. So if there is a Br minus 1 ion, smaller ion, the water molecule with its positive H, it's going to be more strongly attracted to this Br minus 1. Remember, bigger ions, they always make weaker bonds. So this one is going to make stronger bonds. I'll check both of these answers just a second. So for first part was that it's gaseous ions dissolved in excess of water. Stronger attraction with water molecules, it's a smaller ionic radius or a smaller ion, that's the same thing. So that is question number 6. We're going to move to question number 5 now, which is reaction kinetics. So this one is question number 5. There's an equation given. Use the data in the table to determine the order with respect to each reactant. So if I want to figure out the order with respect to, let's say, NH3, which 2 experiments should I compare?
3, 4.
2, 3. Okay, because I want to keep the other variables constant. So 2, 3 is that ClO minus 1 is constant. So it's not going to affect the rate. I'm going to figure out the relationship between these 2. So by what factor did the NH3 concentration, it doubled, right? And what happened to the rate of the reaction? That increased 4 times. So what is the order?
2.
Okay, so
second order.
So it's second order. So the way you're going to write this is if you compare experiments 2 and 3, NH3 concentration doubles. And rate quadruples. So order with respect to NH3. So order, so with respect to NH3, order is 2. So it is second order. So that's the first one. You figured out NH3. Now I'm going to figure out the relationship that will exist between ClO minus 1 and the rate. Which 2 experiments should I compare? I've already figured out that the order with respect to this one is 2. So which experiments should I compare?
So any of them. For 1 or 3 भी कर सकते हैं इसमें.
You shouldn't compare 2 and 3 because then this will get cancelled out. You want to change this, but the problem is that in this case you can't eliminate NH3 because it's changing everywhere. So let's compare 1 and 2. So what you're going to do is you're going to make a rate equation. The relationship for rate would be there's going to be a constant. It's dependent on the concentration of ClO minus 1. and you don't know how it's dependent. So that's X. And it's also dependent on the concentration of NH3. And for that, you know the order, which is 2. So you know one order, but not the other one. You're going to substitute experiment number 1 values into this. If you do that, it's going to be 0.256. And K would be ClO -1 concentration. So that's 0.2 power X. And NH3 is 0.1 squared. And if you find K, so we're going to find K. K would be 0.256, and that's going to be divided by, it's going to be divided by 0.2x, and that's going to be multiplied by 0.1 squared, right? So we figured out the rate constant by using experiment number 1. And then we're going to use the data from experiment number 2, and we're going to put it in the same rate equation. So it's 2.05. That's your rate in experiment number 2. And it's K times ClO -1 concentration, which is 0.4. We don't know what the order is. I think I'm taking the order as X, into NH3 concentration, that's 0.2. And that's going to be squared. So what I'm going to do is I'm going to substitute the K, which K is a constant. So the first constant and the second constant would be the same. So I'm going to take that K and put it over here. So if I do that, it's going to come out to be, I'm going to substitute K. So K from the first experiment goes over here. So it's going to be 2.05. So it's going to be 2.05 into 0.256, and that's going to be divided by 0.2 power X into 0.1 squared. And that's going to be into 0.4x into 0.2 squared. And you're going to simplify this. So this comes out to be 2.05 divided by 0.256. I'm bringing the other things over there as well. That's going to be 0.2 comes at the bottom. So it's going to be 0.2 squared. 0.1 goes up in the numerator. And over here, I've got 0.4 divided by 0.2 power x. So that's 2 to the power x, I guess. So what is this on your calculator? What do you get for this? This is 1/4. Did anyone try this?
Oh, okay.
I'm getting 2.00.
So you're getting 2. So this entire thing is 2, right? So 2 is equal to 2 to the power x. So what is x? X is 1, right? So x over here, the order with respect to this thing, it comes out to be equal to 1, because 2 to the power x is equal to 2. So that's x being equal to 1. So remember, whenever you compare experiments, the first thing is you're going to compare experiments where the other variable has to be kept constant, because you're trying to figure out the relationship between these two. So all other variables must be kept constant. But if the other variable is not constant in any of the experiments, what you're going to do is use the rate equation, whatever that you have, and like you had one of the orders but not the other one. Plug in the values, find the value of K, then plug in the values in the same rate equation. K would be the same. So put the first K in the second equation and you'll simplify and you'll find what this X is. So is this clear?
जी sir, wild guess भी लगा सकते, right?
The first thing is, okay, because if I open the marking scheme will award no marks for all of this. Okay, if I just look at the marking scheme, there would be, this question number 5. There would be absolutely no marks given for all the working over here. For example, look at mark 2, like ClO -1, they're comparing experiments 1 and 2. Actually, they did kind of give marks for the working order, but which came out to be 1 anyway. So they did, I mean, in this case, they are actually giving you marks for the working as well. But a lot of times they don't actually. So even if it's just a 1 mark question. So for finding the second order. So you can, by just looking at the equations and comparing them, you can also figure out the order. Like if you did experiment number 1 and 2, now this thing doubled. It went from 0.1 to 2. So that means the order is 2. That means the rate would have increased 4 times. So from 0.256, it would have increased 4 times to 1.0 something, right? But it is doubling again. So that must be because of this doubling. So we would have figured out that this is order 1 because this is doubling. So the rate is doubling once more. But that is harder to do. It's a lot better to actually do some math and be very exact about your answer. Okay, but is this clear? And we can write the rate equation, which is K ClO -1 concentration. That's 1, and the other one was 2. NH3 was 2. As the next one, use the results to experiment, calculate the rate constant K for this reaction. So I think we already have the K expression. I did, and they were saying use experiment number 1. So I already have the K expression. Just rewrite this, and we found x is 1. So can somebody tell me what the value is? Because we found K already, so that's x is equal to 1.
$128.
Okay, so we are getting
128.
Okay, so we're getting 128, which is fine. And they're also looking for the unit as well. So K would be, use the units that are given in the table. Because a lot of times, or sometimes the unit is not mole per dm cube. Because it's any change with respect to time, right? So over here, you're measuring the concentration change with respect to time, but it could be any change. It could be a volume change. It could be, so make sure you use the units that are given in the table. So the units that are given are mole per dm cube per second. So that's x per second is equal to K into x squared. And you simplified it, it's going to come out to be x minus 2 and s minus 1, and that's equal to K, which is mole minus 2 dm6 and s minus 1. Those are your units. Now, moving on to the next part, on the axis, sketch a graph to show how the value of K changes as temperature is increased. Now, remember that the rate constant only changes with one thing, just like an equilibrium constant. The rate constant is actually kind of linked to the equilibrium constant. And as the temperature increases, the rate constant also increases because if you look at the rate equation, if you look at this rate equation, if the concentration is kept constant and you're increasing temperature and the rate is increasing. So the reason the value of the rate is increasing is because with temperature, K increases. Because you're keeping the same concentration, but the rate is increasing. So that means the K gets affected by the temperature. And it's directly proportional. As the temperature keeps on increasing, the rate constant would also continue to increase. Now, in another experiment, the reaction between chlorate and iodide ions in aqueous alkali was investigated. A solution of iodide ions in aqueous alkali was added to a large excess of chlorate ions and I-1 ions measured at regular intervals. Describe how the results of the experiment can be used to confirm the reaction is first order with respect to I-1. So not really sure what's happening. A large excess of chlorate ions was measured at regular intervals. So you're measuring the I-1 concentration. So that is one thing. The other thing is that chlorate ions are added in a large excess. So that means these other variables are constant. So what you're going to do is, the reaction is between chlorate ions and iodide ions, and they've told you that this is in large excess. So whenever something is in large excess, its concentration kind of becomes constant. So since it's in large excess, now it's this concentration is constant. So so what you're going to do is you're just going to plot a graph of I-1 concentration versus time. That is what you're going to do. अच्छा वो notes किसने कहा था एक second. Just 1 second, let me. This one. So remember the three ways of finding the order of the reaction. So we're looking at the order of the reaction by looking at the shape of the graph. That when you have where's the graph shapes? This one. So remember this. If you plot the concentration of a reactant with respect to time, but you have to keep all other reactants in excess, you want to keep their concentration constant so that the shape of the graph is not affected by the other variables. You want the other variables to be constant. So if you plot the concentration of a particular reactant with respect to time, so by looking at the shape and by looking at the half-life, you can figure out the order of the reaction. So in this case, what you're doing is you plot I-1 concentration versus time. And when you do that, anything described can be used to confirm the reaction's first order. For first order, your shape would be like this. It's going to have a constant half-life. So, so you're going to measure half-life, and it should be constant for a first order reaction. So that should come out to be constant. And then they're asking you to reduce the overall equation for the reaction. Use this mechanism and identify a step as anyway. So they're not asking for the slow step. So deduce the overall equation. So you just add up all of them, add up the reactants and the products. So it's going to be ClO -1 on the left side, plus there's water. Anything that's appearing on both sides is going to get canceled out. So OH -1 is going to get canceled out. HClO would get canceled out. HIO would also get canceled out. So everything kind of gets canceled out. So it's ClO -1 plus I -1, and the products on the other side is Cl -1 plus IO -1. And identify a step that involves a redox reaction. So wherever you see a redox reaction, I think it's not really sure where the redox is happening. It's this one, it's step number 2. I is -1, and on the other side, you've got HIO where I is +1. So that is a redox reaction. And Cl is +1 over here and -1. So step number 2, that's your redox reaction. Okay. So is this clear, this part? We're moving to the...
Yes, sir.
Yes, sir.
So let's move to question number 4 now. So the shapes of the orbital. So identify the type. So that's easy. That's this is P. You got an S, and this one is a D. You have 4 lobes. That's T. Cadmium forms the 2 ions, cadmium 2 plus and cadmium 2 plus. What does this mean? Cadmium diatomic 2 plus and cadmium 2 plus. Anyways, the electronic configuration of cadmium, so this over here, cadmium would be 1 plus actually. So the electronic configuration in these ions is shown. So use this information to explain why cadmium is not a transition metal. So for a transition metal to the main definition is that it should form stable ions. Don't have, the reason it's not a transition metal is that they don't have incomplete
Deception or
desorptions. So which is why they're never going to be colored. State what is meant by the term monodentate. That means it's a monodentate ligand, a ligand that can only form a ligand which forms one dative bond or coordinate bond with metal ion in a complex. In a metal complex or in a complex ion. You've got this reaction, complete the three-dimensional diagram to show the isomers of this thing. So this thing is it's kind of a monodentate ligand. It's 4 CH3NH2s and 2 water molecules. So you're going to draw them, and they're looking for they're looking for 2 arrangements. So there are 2 water molecules. The water molecules could be on opposite sides with their lone pairs. So this one is trans, right? And the CH3NH2s, right? So you had NH2 and CH3. You got another NH2 and CH3, another NH2. And CH3. Anyway, so this is 4 CH3NH2 ligands, and there's 1 water molecule. They actually they said that use L to represent this. So we drew the whole thing. And this entire thing will have a charge of +2. So what is the other isomer? The other isomer would be that the 2, so you're going to draw the other one. The other one would be that the 2 water molecules are not 180 degrees apart, they are 90 degrees apart. Okay, is that clear? So this one, so the other one would be that the 2 water molecules are either 180 degrees apart or they are right next to each other. So those are the 2 isomers. One of them is cis, the other one is trans. State what is meant by the term stability constant. So again, that's a definition. The definition of a stability constant is that it's an equilibrium constant for the formation of a complex ion in a solution. That's what they're saying. So so whenever you're making a complex ion in a solution, the equilibrium constant for that is your stability constant. So you should actually write this definition. That's so it's the equilibrium constant for the formation of a complex ion in solution. So in any aqueous...
What is... Sorry, what was partition coefficient?
The partition coefficient was something totally different. That was when you have 2 immiscible, it was the ratio of the solubility of a solute in 2 immiscible liquids. Like if you had oil and you had, let's say, water, and there's some salt, let's call that X. So there would be some amount of X dissolved over here, and there would be some amount of X dissolved in oil as well, right? And the particles would be in equilibrium along the partition. They would be moving from the oil layer to the water layer and from the water layer to the oil layer, right? So it was X in oil in equilibrium with X in water, right? So it was the Kc of this. That was partition coefficient. So you call that Kpc. And it was the concentration of X in water. That's your product. And divided by the concentration of X in oil. And you calculate that. So that was what Kpc was, partition coefficient. Okay, clear? So, but this one, equilibrium constant for the formation of a complex ion in a solution. So in any aqueous solution, if you do ligand exchange and another complex ion is formed, this is a reversible reaction. The Kc product over reactant, that's basically your stability constant. When it has a bigger value, that means ligand exchange will happen. When it's a very small value, that means the ligand exchange will not happen. So that is stability constant. Complete the table by placing one tick in each row to describe how increasing temperature will affect K stability and the equilibrium concentration of the cadmium complex. Now, they've given us the enthalpy change. It's a reversible reaction, right? So, and Kc, remember, changes with temperature. So if I increase temperature, which reaction would be favored, forward or backward, according to Lee-Shatler principle?
Backward.
Backward.
Okay, it's an exothermic reaction, right? So that means the backward one is an endothermic reaction, right? So when you increase temperature, the backward reaction is going to be favored, which means Kc value, would it increase or decrease? And will you
Decrease.
I mean, if you do products, you get more reactants, right? So that means it's going to be a smaller value. So it's going to decrease. So that's your answer. K stability value, what? It's going to decrease. And you're going to write that the equilibrium favors endothermic at higher temperatures. They talk about higher temperature, right? Increasing temperature, right? So equilibrium favors endothermic, which in this case would be, it's going to be the backward reaction. And what happens to the concentration of this thing? So since it is moving backward, the concentration of this thing would also be lesser, right? So not only does K stability decrease, but there's a reversible reaction, backward reaction is favored. So less complex would be formed. Okay, is that clear?
Yes, sir.
As the next one, this is about ETA. It's a polydentate ligand. When a solution of ETA is added to this thing, a new complex is formed. The values of the stability constant for two cadmium 2+ complexes are shown. Fine. So you're given these values. What does a higher value mean? Will this be formed or will it not be formed?
Stable, yes. This will be formed. EDTA.
So that means it's got a lot of products forming, a lot of ligand exchanges happening. So there's a much bigger chances of this one getting formed. It's more stable. This one, less of it would be formed. Like if I add, so solution containing equal moles of this thing and this thing are added to, so you're adding it to a solution, aqueous solution. Will EDTA knock out those ligands and take their positions, or will CH3 NH2 knock out the water ligands and take their positions? EDTA has a much bigger K stability value. So that means EDTA is going to win. It's got a much bigger value. So predict which of the complexes is found in large amounts. So it's this one, the one that I've ticked. And explain your answer.
Yeah.
So the explanation would be it's got a bigger value, so more products would be formed. Is that clear?
Yes.
Sir, complex
Yes, sir.
signs may I have question here. At
Oh.
times they ask us to predict the shapes of a complex. I mean, let's suppose they tell us to predict how would this complex look like. Yeah, structure banana. So in that case, how do
first thing is it's not going to be an open-ended question. It's very specific questions. It's very specific complexes that are going to be asked. But the rest is if something unknown comes. Here, for example, this is transition. So if something unknown comes, just count the number of bonds. Like the valence shell electron pair repulsion theory. So if there are 4 bonds, so that is obviously tetrahedral. But there are some examples where 4 bonds are actually square planar as well. So you have to remember the complexes that have written down in the notes over here. For example, for square planar, remember cisplatin and transplatin, they're square planar. They have 4 bonds, but it's square planar. The other ones, remember that with the ones with Cl and water and with this one. With water, you should know that it's octahedral. With NH3, it's still octahedral. With Cl, it's tetrahedral. With this one, it's again octahedral OH ions. So you've got to remember this, especially the ones that we've written down in the notes. So the next part is he's saying methylamine is a process. Clear hai wo pichla?
जी sir.
Achha, methylamine is a base. So why is it a base? Because it's got a lone pair. He's saying write an equation, so it's going to accept an H+1 ion. It will become CH3 and NH2 plus 1. Methylamine is a useful reagent in organic chemistry. Write an equation for the reaction of ethanol chloride with methylamine. Now that is this thing. Okay, like if you look at the, so that one is amide linkage. I'm gonna open this one. So that one is amide links. Amide links are formed with acyl chlorides. So just 1 second. So for example, over here you've got an acyl chloride COCl. You add NH2 to it, it will end up forming. You'll end up with an amide link. Acyl chlorides and amines, they end up forming amides. So this is what's going to happen if you have methylamine and it's CH3 NH2 and N has lone pairs, and you've got an ethanoyl chloride, so that's CC double bond O and Cl. So the carbon is really strongly positive. So these lone pairs and this carbon, which is strongly positive, they're going to get attracted to it. The H and the Cl would be lost. They would end up forming HCl. And an amide or peptide link would be created between the C double bond O and the N. So that is your molecule that's going to be produced. And the byproduct would be HCl. So deduce the type of reaction being shown over here. So
ऊपर reaction में आपने तो कुछ नहीं लिखा हुआ. I mean, it should have been NH3 और आपने reactant ही लिख दिया सर.
अच्छा sorry, ये किसकी बात कर रही है इसकी? This one?
जी.
There should have been NH3 plus 1 because I'm adding an H plus 1, so it should have been NH3. Yeah, that's fine. Now, methylamine also reacts with propanone to form P. So that is methylamine, and he's saying deduce the type of reaction. So what is the reaction where a water molecule gets produced?
Condensation.
Because this one is condensation.
Elimination.
And so that's this one. Let's move to the previous question. We've got so this one is about I think electrochemistry. So the reduction of chlorate with SO2 forms ClO2. So ClO3 minus 1 with SO2 ends up forming ClO2 and sulfate ions as the only product. So that's easy. I mean, you just have to balance this. Remember, sulfur is +4. This is +6. The electrons gain and loss must be made equal. So that's a loss of 2 electrons, right? Cl over here is, I guess it's +5. You can just double check it. Cl over here is +4, right? So that is a gain of 1 electron, right? So who should I multiply with what number?
SO2 with 2.
This is going to be multiplied by 1.
ClO3 multiplied.
This one would be multiplied by 2. So it's going to be ClO3. This is going to be multiplied by 2. Explain using this reaction as an example what is meant by disproportionation, where the same element, +4, this is +3, I guess, and this is +5. So same element gets oxidized and reduced. And you can write that ClO2 goes to +3 and also +5. Gets reduced to +3 and gets oxidized to +5. Deduce the Ionic equation for the reaction in B1, this one. So we're going to write the Ionic equation. So in the Ionic equation, deduce the Ionic half equations for the reaction. So we need to split it up into two equations. There's going to be an oxidation equation and there's going to be a reduction equation. So let's talk about the Ionic half equation, the oxidation equation. So +4 to +5. So that is ClO2, which goes from +4, and it ends up with, you end up with ClO3 -1, where Cl is +5, right? I mean, you're not going to write this +4 and +5 because I'm just writing it for working, but I'll remove it at the end. So I've written down the oxidation states on top of them. So if something goes from +4 to +5, that means it has lost one electron, right? So you add in the one electron.
Mhm.
And then you have to somehow balance the oxidants. Now you can't really balance the oxidants because the Cl will get unbalanced. So you've got two things over here. You've got your OH ions and you've got your water molecules. So you need to sort of use them so that the oxidants, I mean, these are spare atoms in the entire equation, which are not taking part in the redox reaction. So you're going to use those to balance this equation. So there are more oxidants on this side, there are fewer oxidants on this side. So what I'm going to do is I'm going to bring in some OH ions, right? And let's say I bring in one OH ion, right? If I bring in one OH ion, then on the other side, let's say I bring in two OH ions. And there's a water molecule on this side. Are the hydrogen and oxygen balanced now? You got four oxygens and you got 4 oxygens over here as well. 2 hydrogens and there are 2 hydrogens on this side. So that kind of sums it up. That balances it. You can remember to use them as for balancing purposes, to just balance out the atoms. The other one is we're going to focus on the reduction equation. So the reduction equation is going to be, it's going to be ClO2 going into ClO2 -1. So that's easy because the atoms are already balanced. ClO2 turning into ClO2 -1. So that is +4 to +3. That's a gain of 1 electron. So 1 electron gained. I just remove the oxidation numbers. So those are my two half equations. Is that clear?
Yes, sir.
So then the next part is that lithium iodine electrochemical cell can be used to generate electricity for a heart pacemaker. The cell consists of lithium electrode and an inert. I mean, lithium. Remember this, just a very generic question that usually comes. It's about lithium batteries. Just remember that they are very compact. They use in cell phones, etc. So they carry a lot of charge. So heart pacemaker, they're long lasting as well. The cell consists of lithium electrode and an inert electrode immersed in body fluids. When current flows, lithium is oxidized and iodine is reduced. Fine, use data booklet to write half equations for the reaction taking place. So iodine is reduced. There's only one equation in the data booklet for iodine, that's this one. And that's 0.54 volts. And there's only one equation for lithium, which is this one. Lithium is +1, gains 1 electron, forms lithium. Not really sure what the value is. So we'll just look it up for lithium. It's this one. This is minus 3.04 volts. So who gains electrons, who loses electrons? The lower one loses and the higher one gains. And you need to balance the number of electrons. So I multiply lithium by 2 and I add up the reactant. So it's going to be I2. In the second equation, the reactant is 2 Li. And my products in the first one are 2i - 1. In the second one, my products are 2 Li plus 1. And we can calculate the E0 cell. So that's a pretty high E0 cell. It's higher potential or reduction potential, which is 0.54. minus the oxidation potential or the lower potential, which is minus 3.04. And that comes out to be 3.58 volts, I guess. Is that clear? Clear? Yeah.
Yes, sir.
G.
Just 1 second. So the next part, you've got current 2.5 into 10 to the power minus 5 amperes drawn from the cell. Calculate the time for 0.1 grams of lithium electrode to be used up. So 0.1 grams, how many moles is that? That's 0.1 divided by what is lithium? That's, I guess that's 7. Not really sure, or something close to 7. So lithium is 6.9. So lithium over here is 6.9. So tell me how many moles do we have for lithium, and make sure write your workings properly. So even write the. So what do we
0.0145.
So we got these many moles. And how many electrons are needed to deposit this much lithium or get rid of this much lithium? That is 1 lithium loses 1 electron, right? So you can figure out the moles of electrons. That's going to be the same, right? 0.0145 moles of electrons, right? Because 1 lithium loses 1 electron. Now, you know that 1 mole of electrons has how much charge? That's got 96 Faraday constant. That's got 96 500 coulombs. Using the same ratios, you can figure out the coulombs for this one. What do you get? 0.0145 into. So what do we have?
1899.
1899?
No, 1399.
1399. Right?
What? Yes, sir.
So we got 1399 coulombs, right? So since we've got 1399 coulombs, yeah,
Divide the current.
you just
So
what was the question? You had to calculate time, right? So Q is equal to IT. So charge divided by current, right? So it's 1399 coulombs, and that's going to divide by the current, which is 2.5 into 10 to the power minus 5 amperes. So that's a lot of time. So you're back. Kitna hai?
5.6 into 10 to the power 7.
Yeah, that's a lot of time for the lithium to get discharged. And that's it. That's question number 3. I'll just take the after 10 minutes. I'll take P4. I'll do a P5 paper. Okay? So we'll continue tomorrow then.
Hello.